Good day everyone, Mr. Armke back with you for Net 125. Today we're going to be talking about Module 6, the data link layer. So let's jump right in. The data link layer is the direct interface between the logical and physical aspects of the network interface. So we're going to talk about how media access control in the data link layer supports communication, how it facilitates it. So we're going to look at three things: the purpose of the data link layer, different topologies with which we will interact, and the data link frame. So the data link layer is responsible for communications between end device network interface cards. So there's a NIC on your host machine that you're using right now, and there's a NIC on the server that you're accessing this video from. And whatever intermediary devices exist in between, there is an interface port as well. So this layer is going to allow upper layer protocols, layer 3 and up, to access physical layer media at layer 1. It's also going to encapsulate layer 3 packets for IPv4 and IPv6 into a layer 2 frame. It also performs error detection and rejects corrupted frames. So the data link layer is able to identify, in certain capacities, a frame that is not considered valid for purposes of processing or transmission of data. So the IEEE 802 LAN/MAN standards are specific to the type of network being employed. Is it Ethernet? Is it using a wireless LAN, a wireless personal area network such as Bluetooth? The data link layer itself is not a continuous single layer, but rather a marriage of two sublayers. The two sublayers are the LLC, the logical link control, and the media access control, or MAC. The LLC is going to communicate between networking software at the upper layers and device hardware at the lower layers. The MAC sublayer is responsible for data encapsulation and dealing with media access control, of course, with the MAC address. So we can see here in the graphic to the right that we see layer 3 above, layer 1 below, and then the interaction between the LLC and the MAC. The LLC sublayer has its own 802.2 standard according to the IEEE, and that is what deals with interfacing with layer 3. And then the three I just discussed for the MAC sublayer: Ethernet 802.3, WLAN 802.11, and WPAN 802.15. Now, packets exchanged between nodes may experience numerous transitions between data link layers as well as different types of media. You could have a data transmission that goes from a wired host to a router. That router hooks back to an ISP. That ISP transmits something to a satellite. That satellite bounces over across the other side of the planet. It's received by a secondary ISP there. That ISP connects to another wired connection, bounces to a Wi-Fi connection at a host site, and then connects to another device. So we can see a number of transitions that occurs. Now, at each hop, routers are going to perform 4 basic layer 2 functions. Number 1, the router is going to accept a frame from the network, the medium as it were. So if it's a fiber optic line, copper line, Wi-Fi, whatever. It will then de-encapsulate the frame to expose the packet. So remember, we talk about PDUs being named different things as they graduate between different layers. We go from a segment to a packet to a frame. So we're going to peel off the frame, the MAC header, and we're going to read the IP address. Then we're going to re-encapsulate it into a new frame using our new existing start point as our instigating MAC address, our source, and then we're going to have the same destination that we would for our next hop. And it's going to forward the new frame onto the next segment in the 4th step. Now, data link layer standards and protocols are traditionally defined by nonprofit engineering organizations. These are organizations that derive very little by means of actual funding, but they do allow consensus between different international agreements, so that, you know, somebody in France and somebody in Britain, somebody in China, somebody in the US, somebody in Brazil can all sit down and talk and say, okay, this is what we're going to agree upon for the Ethernet standard, the Wi-Fi standard. So the IEEE is the Institute for Electrical and Electronic Engineers. The ITU is the International Telecommunications Union. The ISO is the International Organizations for Standardization. The American National Standards Institute is called the ANSI, or ANSI, as I learned it. Next, let's talk about topologies, how we arrange these things. First things first, when we talk about the topology of a network, it's the arrangement and relationship of network devices and the connections between them. Now, there are two types of topologies we traditionally use when describing a network. The physical topology deals with physical connections and how devices are linked. The logical topology talks about virtual connections using device interfaces and IP addressing schemes. There are three common physical WAN topologies that we discuss: point-to-point, hub and spoke, and mesh. Point-to-point topologies are the simplest and most common. This is a permanent link between two endpoints. So when we talk about like a bus topology, for instance, that's traditionally going to be a backbone that connects to individual items. This is even simpler than that, to where we have, let's say, a crossover cable that connects two desktops. Hub and spoke is what we talk about when we're dealing with a star topology, where we have a central interconnection that branches through different point-to-point links. So a hub and spoke is actually made up of several point-to-point connections. The mesh is very high availability, but requires every end system to be connected to every other. So if we have a group of 6 computers, each computer has to have 5 connections, one to each of the other partner computers in that group. This is great for making sure there's lots of redundancy, and in the event of a particular network device failing, that the rest of the network can go forward. But the amount of overhead that is required to maintain those connections can be very, very difficult to maintain, especially with scalability. Now here we are with a physical example of the point-to-point topology. We have a router at node 1, a router at node 2, and then a various collection of interconnectivity devices and mediums to go between them. The nodes may not share the media with other hosts, so this is a dedicated connection. Because all frames on the media can only travel to or from the two hosts, point-to-point WAN protocols can be very, very simple. We don't have to worry about routing in the same capacity. End devices on LANs are traditionally interconnected using a star or extended star topology, as you can see in the top two graphics on the right. They're very easy to install, they're very easy to scale, and they're very easy to troubleshoot. Early Ethernet and legacy token ring topologies also provide two additional topologies: the bus, which is where we have all of our systems linked together and terminated on each end. And then we have what's called a ring topology. This is where we have a system that is connected, basically pass it to the left kind of argument. That's how I always heard it. So you have one device daisy chained into another to form a ring. And usually you have a token that is generated by the network interface in order to identify who can communicate at any given time. It's a type of collision avoidance. Now, when we talk about topologies, we have to talk about modes of communication. There's half duplex and full duplex communication. There's also what we call simplex. Simplex is very easy to understand if you think about like a radio station. The radio in your car is a receiver. The radio station has what's called a transmitter, and each of them only do that one job. There's no switching. With half duplex communication, we can send or receive, but we can only do it one at a time. So that's much more than what we expect to see for something like a walkie-talkie. This is what we use on wireless LANs as well as legacy bus topologies with hubs. Full duplex communication is what more of us are used to. It's very much like a standard telephone conversation where you can simultaneously transmit and receive on the same medium. Now this does mean that there's potential for collision. There's a lot of overlap potential. So we have to make sure that we have collision avoidance and detection methods. Contention-based access is one of the control methods we use to carry this out. If we have all nodes operating in half duplex competing for the use of a medium, we have contention-based access. They are contending with one another in order to try and get their messages out. So an example of this would be what's called CASMA-CAD, CSMA/CD, Carrier Sense Multiple Access with Collision Detection. That is a bus topology Ethernet tool. It's legacy. It's not something we use as much anymore. In the modern sense, we tend to use what's called Carrier Sense Multiple Access with avoidance rather than detection. So that's CASMA-CA. That's used on wireless LANs. Controlled access is a little bit different. This is, again, a legacy system. It's deterministic in that every node has its own time on the medium. That's the timing token I was telling you about. So things like Token Ring and ArcNet would use controlled access. So CAD is used by legacy Ethernet LANs and operates in half duplex. It will then use collision detection, essentially finding fragments or things like that, in order to govern how transmission will go, as well as the response to collisions. It'll transmit what's called a jam signal if there is a necessary link for that, or they will have what's called a time interval, where they will, after detecting the collision, wait to transmit the data. The random period of time is usually staggered so that they don't wait for the same random period of time and then create a second collision. CASMA-CA operates in half duplex using collision avoidance instead of detection. So when transmitting, we include the time duration needed for the transmission. Kind of like if somebody were to, and this is dating myself, of course, in the days of landline telephones, if you were on the phone, you were having a conversation, and somebody else picked up an extension of that line in the same house, you'd be like, hey, I'm on the phone, give me 5 minutes. You know, giving them that, like, I'll be done as soon as I can, da 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 da. Other devices on the shared medium receive that time duration and then know how long the medium will be unavailable. So it's almost like having a reservation or knowing when the next showing of a particular movie is at the theater. It's just setting that expectation. Now let's take a look at the data link frame itself, the actual transmissible segment of information. So data is encapsulated by the data link layer, layer 2, with a header and a trailer. Now this is the only portion of the encapsulation process for the OSI model that involves a trailer in addition, because it's the end of the line. After it leaves the data link layer, it then moves to the physical layer and is transmitted as bits. A data link frame has 3 parts: the header, the data, and the trailer, the fields of which will vary according to the protocol being used. The amount of control information carried within the frame varies according to access control information as well as the logical topology. What you'll find is that the logical topology, is really what demands the most processing or planning when we're dealing with protocols. So here we can see a kind of a breakdown of the simple fields that we'll see as part of the frame. In the header, we'll see the frame start. In the trailer, we'll see the frame stop. We'll also see addressing, which indicates our source and destination MAC addresses. The type is going to tell us what type of layer 3 protocol to expect. Is it going to be TCP? Is it going to be UDP? I'm sorry, that's layer 4. If we're talking about IP protocols, we're dealing with type there. Flow control services, that's going to be in the control field. Again, flow control services, if we're talking about TCP IP, will exist at multiple layers. The payload itself exists in the middle, and then error detection just before the frame stop, usually using what's called a CRC, or cyclic redundancy check, just to make sure that the data that was sent is in fact legitimate, that there's no dropped portions. Helps us to determine if there's an error. Layer 2 addresses, also referred to as a physical address, are contained in the frame header and are used only for local delivery of a frame on the link. They are updated by each device that forwards the frame, so that means as it goes from our host to R1, our source is going to be that first host, and the destination will be R1. When it arrives at R1, we then change the source MAC address to the MAC address for R1's outgoing interface. Then our new destination is the next router in sequence R2. Same thing happens at R2, except that's the new source, and then the web server is the new destination. So something that's interesting is that in a frame, the MAC address will change, although MAC addresses intrinsically stay the same based on the device. On the other hand, the IP address, which is something that we can change locally, will stay the same in the frame. The logical topology and physical media used will determine the link protocol that is used. So if we're talking about wireless, Ethernet, standard point-to-point, or what's called triple P, HDLC, high-level data link control, or what's called frame relay, very simple structural thing, but occasionally used, very, very rarely. Each protocol performs media access control for specified logical topologies. I will say, pretty much in my experience, Ethernet and wireless are all we really see. And that is Module 6. It was short, sweet, and to the point, I hope. Kept it under 15 minutes. If you have any questions, of course, you can contact me via email at jearmke063@cfcc.edu. you can always contact me directly through Blackboard, or if you need to, you can contact me at my Google Voice number, which is, of course, 910-239-7814. Have a great day, guys, and I'll catch you next class.